Women in Hyperbolic 3 Space.
Good afternoon, everyone. I'll be presenting some work I did over the last summer at my RAU at UC Berkeley. So this is the overview of my presentation today. First, we'll be looking at the models that describe hyperbolic 3 space, and then we'll look at the purpose of our project in detail, and in the end we'll demonstrate the construction of a convex ideal cube in the form of answering to our question. So first, models of H3. So hyperbolic geometry has a different set of rules compared to Euclidean geometry. But since we have a time constraint today, let's not get into too much of the detail. And I think it'll be better to just jump right into the models that describe hyperbolic 3 space and get a feel of how the objects are represented or described in these models. So the first model is the upper half space model. It's defined in the upper half of a 3-dimensional space. And in this model, hyperbolic angles are the same as Euclidean angles. So the 90-degree angle you see in the image there is, in fact, 90 degrees in hyperbolic space as well. And secondly, hyperbolic lines are half lines that are vertical to the complex plane, which is the boundary of this model, and also circular arcs that are orthogonal to the boundary. Hyperbolic planes are half planes that are vertical to the complex plane, and also spherical caps that are orthogonal to the boundary. And the first one you can, in figure 1, the one with the circular arc, it's a semicircle, and the other one, the one on the right, it's a hemisphere. So the next model is the ball model. It's defined on the interior of a unit sphere. Similar to the previous model, the angles in this model are the same as Euclidean angles, and lines are spherical diameters and also circular arcs that are orthogonal to the boundary. Hyperbolic planes are Euclidean planes that go through the center of the sphere, and also spherical caps that are orthogonal to the boundary. So as we kind of went through what lines and planes how they look like in these models, hopefully it's not surprising when I say this is a hyperbolic cube in the ball model. So you can see that each face is curved, that's coming from the faces belonging to the spheres, and each line belongs to a circle. So now, our question. Given a set of appropriate internal dihedral angles, how do we construct a convex ideal polyhedron in hyperbolic 3 space? So there are some terms that may not be familiar to some people, so we'll go over that in the next slide. A convex polyhedron is a polyhedron such that when you pick 2 points in the polyhedron and draw a line that connects those 2 points, that line is contained in the polyhedron. It doesn't leave the polyhedron. An ideal polyhedron is a hyperbolic polyhedron such that all the vertices are on the boundary of the ball model. And also in the question I wrote, given an appropriate set of internal dihedral angles, what I meant by that was that we're going to use a set of internal dihedral angles that guarantees us the existence and uniqueness of a convex ideal polyhedron that has those internal dihedral angles. And that set is coming from a theorem that we went over last summer, but we're not going to get into the detail of that theorem. And also, isometries are distance-preserving maps. For example, on the Euclidean plane, isometries are reflections, rotations, translations. So basically, you plug in 2 points to an isometry, then the distance between those 2 points in the pre-image is the same as the distance between the images of those 2 points. So now, going back to our question again, hopefully it makes more sense now. Given a set of appropriate internal dihedral angles, how do we construct a convex ideal polyhedron in hyperbolic 3 space? So it is hard to answer that question in its entirety, so we'll be partially answering that question by demonstrating the construction of a convex ideal cube in hyperbolic 3 space. So before I get into the detail of the demonstration, I want to clarify one thing. So a cuboid is a polyhedron that has the same combinatorial structure as a cube. So it has 6 faces, each face has 4 edges, and each vertex is incident to 3 faces. So from now on, I'll be using the word cube to mean cuboid. So it's like a more general idea of a cube. So now, So we looked at, there are other models that describe hyperbolic 3 space, but we looked at the ball model and the upper half space model. And when we started working on this project, we had to decide in which model do we want to complete our construction. And we decided to do it in the upper half space model because we thought the calculations would be slightly easier compared to the ball model. Those were the two we were considering working in. However, the problem was, although we have an idea of what a cube looks like in the ball model, we didn't know how it looked like in the upper half space model because the lines and the planes are defined differently. However, considering a map that preserves all the information, takes everything in the ball model to the upper half space model while preserving all the information such as angles, lines, planes, we found out that if we had a cube with vertices identified as in the image on the left, in the upper half space, the same cube is defined as the image you see on the right. And this appropriate transformation I just said, the one we used was a composition of a transformation called Euclidean spherical inversion, and also we use planar reflection. We're not going to get into the detail of that transformation, but if you're interested, you can come to me after the presentation. Okay. So now, right now at this point, we know where the vertices of the cube would be on the complex plane, combinatorially, I guess, but we don't know their geometric locations. So we want, and the information we have right now is the internal dihedral angles. So we want to somehow use that information to say something about the geometric locations of the vertices. So these are the lemmas we proved during the project in order to use the internal dihedral angle information to say something about the stuff on the complex plane. So if we have, this is all in the half space model, by the way. So if we have a dihedral angle alpha made by two planes, that angle alpha, and those are hyperbolic, those are Euclidean planes that are vertical to the complex plane, by the way. So if we're making a dihedral angle alpha, that angle is equal to the angle made by the lines that are at the base. And that's because in hyperbolic space, or in this model, hyperbolic angles are the same as the Euclidean angles. So you can just think of a Euclidean translation of the angle. You just bring alpha down. And in the middle, you have angle alpha made by the plane and the hemisphere. That angle is equal to the angle made by the baseline of the plane and also the tangent line of the base circle at one of the intersections of the line and the circle. In the last picture, we have dihedral angle alpha that is equal to the angle made by the tangent lines of the base circles at their intersections. So, taking these results into account, if we identify the angles of convex ideal cube in upper half space as in the image on the left, all that dihedral angle information would appear on the complex plane as in the image on the right. Let's take that in. Okay. So now at this point, we have the three angles that is determining the outermost triangle, that is ACE. So we know the locations of those vertices up to isometry at this point, but we don't have enough information to determine the positions of the rest of the vertices. So in order to figure those out, we drew additional edges, which are represented as dotted lines in the picture, and we also identified the angles made by those dotted edges and the already existing edges, which you can see as A, B, C, D, E, F in the picture. Those are the angles we identified. So then, after doing that, using results from Euclidean plane geometry, we'll have the system that you see on the right. And as we reduce that, we'll get this system. And at this point, f is still a free variable. But if any of you remember, this convex ideal polyhedron is supposed to be determined uniquely. So this f value needs to be unique. So we cannot stop here. And as we were experimenting with different values of f, we found out that this triangle you see in the middle, FBD, was not forming for the values of f we were trying. So the f prime vertex you see should be coinciding with f, but it wasn't. So the condition we needed was OF equals OF prime. So, and looking at the image on the upper left and considering a relationship between OF prime and OF, the equation on the third line is a relationship we know between those edges. And since we want OF equals OF prime, the equation you see with the underline was the last restriction we needed to have to determine f. So as we solve this equation in terms of f, we get a unique value and we're good. So at this point, we have all the angles, the right angles. We have all the right angles in that image. So that means we know the locations of all the vertices up to isometry. So we're pretty much done at this point, but not yet. Okay, so let's say this was our given set of internal dihedral angles, and from here we want to complete the picture, complete the visualization, if you may. So since we were discussing things up to isometry until the previous slide, we need to fix the length of one of the edges in the picture. So we fixed A and B at those coordinates. And then we wrote a Python code from scratch to visualize the convex ideal cube that has those internal dihedral angles. And this is in the upper half space model. And the same cube in the ball model looks like this. And this is zoomed in. It looks a little bit weird because of that aspect ratio. But yes. So conclusion. We also worked on building convex ideal octahedron, so the generalized version of octahedra. But we're not going to show that today. But we hope that we can extend this method for other generalized version of polyhedrons. But we may have more nonlinear equations. The equation we had to use to find the unique f value was nonlinear. So for the other more complex polyhedron, we might have more of those, and that might be an issue to be solved. Reference. Okay. Thanks to NSF for funding the RU at UC Berkeley, and thanks to my RU mentor Franco Vargas Payete for his kindness, and thanks to the conference for letting me come here and give this talk.